Welcome to our series in conversation at the EPFL Pavilions, Amplified for Art, Science and Society at the Swiss Federal Institute for Technology in Lausanne, Switzerland. My name is Giulia Bini. I'm curator and producer at the EPFL Pavilions, and it's a great pleasure today to have an episode of our In Conversation series, in conversation with artists Melissa Dubbin and Dubbin and Davidson, Professor Auke Ijspeert and Jonathan Arreguit, Ph.D. at the EPFL. Our talk today will be devoted and dedicated to a very special production that we realized in the framework of the exhibition titled Delay Lines Feedback. And this work was pretty exceptional, a work by Melissa and Aaron, which was realized in the framework of a remote artist in residence program at the EPFL Pavilions, with the great collaboration of the EPFL Biorobotics Laboratory and Professor Auke Ijspeert. So before entering the discussion and understanding really the many layers of this very special production that we realized in the framework of our exhibition, Nature of Robotics, an Expanded Field, I would like to introduce you to a small excerpt which can give you really the feeling of the space and the installation in our space during the exhibition. So, Melissa and Aaron, you have been chosen in 2020 last year as artists in residence program at the EPFL Pavilions. You are based between Brooklyn, New York, and California, and you apply collaborative processes in your practice and engagement with materials. Your work are characterized by transformations of the biological and the mechanical. And precisely as we could see in the video, Delay Lines Feedback was a very, let's say, complex and sophisticated installation that we realized, especially for Nature of Robotics. Of course, as we could, let's say, see shortly in the image, the protagonist, we could say, of this installation is a soft Manta ray, a soft robot, that you realized actually already originally at the origin of your research in soft robotics, which started in 2019 in the framework of the Okayama Art Summit. I would like now to enter a bit the very special collaboration that we could realize in the framework of Nature of Robotics. I would like to ask you a bit of the genesis of this work and this idea, which is, I mean, what brought you in including soft robotics in your practice.
Did you want to talk about soft robots?
Yeah. Do you want to start with delay lines or?
The genesis of delay lines. I think it's
okay. So delay lines. The title comes from a long-standing interest we have in these physical structures or objects that can be used to delay information or sounds. And that comes out of our interest in working with sound and audio and thinking about how you have these ways of essentially kind of holding something for longer than you would be able to normally. So a delay line allows you to kind of hold on to something and then do something with it. And they are often these very kind of beautiful physical structures where it's very apparent that something is being delayed. And that kind of allows this synchronization of maybe non-biological entities, right? This way of kind of synchronizing things. So that's where the delay lines comes from, and you kind of see that manifested in the glassware. The soft robots.
The soft robots, I would say, I mean, robots in our own work, we in I think we didn't start with soft robots. We began just looking at robotics, and we got interested in the protective garments for robots, these kind of robot suits that protect a robot that's painting a car, for example. And the reason we became interested in them was not only how they kind of anthropomorphize these robots, but also they, in the case of a painting robot, created these traces or imprints of time and of the labor of this machine. So that was where one of the projects that we did in, I think, 2014 or 2016 actually, Robochrono Choreo. And then we also were interested in kind of robots that learn. And we had this robotic arm that was learning from a child who was drawing with it. And then the robot would reproduce this drawing, and we had it reproducing it in grains of iron and kind of using magnets to create this drawing with the robotic arm. So that was maybe our first works where we were kind of collaborating with robots. And then when we were invited to participate in the Okayama Art Summit in Japan, we met with the Systems Integration Lab at Okayama University and looked at all of the robotic work they were doing, specifically the soft robots. And when they showed us this Manta ray that they had made, I think it was one of the first soft robot Manta rays made in 2012, 2013, we became very fascinated with it because it hadn't found its practical application and had not been, developed any further. And also, it was one of the only soft robots that was the full creature. It wasn't the disembodied arm of an octopus or the disembodied human hand or something like that. So something really maybe a form of empathy, because the whole creature is there, we felt this connection. And also soft robots became really interesting because they're powered by air. So this idea of, in our work, trying to make tangible or work with these forces or phenomena like magnetism or sound or air that we can't see. So we were interested in how this soft robot, you can relate to it because it's breathing in a way, and this relationship to life through movement and breath. So that was how we began. And what you've been seeing as I'm talking is some documentation of the installation that we made in Okayama for the Art Summit.
And thanks a lot, Melissa and Aaron, for this introduction. What I think indeed was extremely interesting also during the research process for Nature of Robotics, we wanted, of course, to focus on what we named the new paradigms of robotics. And at the EPFL, so from the scientific and engineering perspective, these were the field of bio, soft, and reconfigurable and micro biorobotics. And it was very interesting in, of course, discovering your work and understanding what we could say more a tangential interest in robotics that arrived, let's say, out of a broader artistic research that you have. And we really thought that it would be very interesting to think about this work also in the very specific context of the Swiss Federal Institute for Technology in Lausanne. And we could realize, we could say, a new version of the work with the title Delay Lines Feedback, in collaboration with scientists and professors at the EPFL through, let's say, the support of the College of Humanities. We really sort of promoted this exceptional collaboration. And so during the process exactly of thinking how to realize this project at the EPFL in a very specific framework, which was, of course, the COVID pandemics, and therefore the necessity of conducting this research and this project remotely, we had the great pleasure to collaborate with Professor Auke Ijspeert and the Biorobotics Laboratory at the EPFL. And I have to say, it was, of course, a challenge to find a way to develop this collaboration at the EPFL, and it was amazing that we could establish this dialogue through, of course, the work of Melissa and Aaron, but also, of course, through the specific research conduct from your laboratory at the EPFL. Therefore, I would like to discuss now and to go through the reasons why, let's say, the work of Melissa and Aaron could immediately sort of resonate with the directions developed by Biorobotics at the EPFL.
Yeah, great. So for me, it was super exciting to collaborate with Melissa and Aaron, because everything related to movement, water, and delays, I find it interesting. So in my lab, we had a Biorobotics lab. So we are very much fascinated by locomotion, especially animal locomotion. And one thing we like a lot is to use robots to investigate animal locomotion. So here, for instance, what you see is a Salamander robot that we developed together with neuroscientists. And this robot was really developed as a scientific tool, a tool to investigate how the nervous system of animals control their locomotion, and to see how it can adapt to different environments. And salamanders are very interesting because they're amphibian, they can swim and walk. So here you see the water component. And the robot also has soft components. It's a hard robot, but it also has soft connections that mimic a bit what is in the Manta robot from the display. So now what's interesting for me is indeed exploring how the nervous system interacts with the body and how this has changed during evolution. So how have animals changed from purely swimming to swimming and walking, and finally to mammalian-like walking, as we see in cats and in humans. And I really like the notion of using a robot as a scientific tool. One thing that also I find interesting is if you stop the video, you see that the robot itself is just nothing. It's just pieces of blocks connected together with motors. So the appearance is really not interesting at all. And what makes it lifelike is the motion. So it's really when it moves that you starts realizing, oh yes, this is quite close to what the animal does. And in fact, it's very close where we really quantify that. So that's something I really love in my lab, is to use the robot as scientific tools. So that's the first mission of the lab. A second mission of the lab is to apply them for instance, field robotics, to do like search and rescue or pollution monitoring or help with agriculture monitoring. So we still have a problem of having robots that can go outdoors. And here I think taking inspiration from animals, make robots that can swim, crawl, is really one interesting way forward. And that's one thing we find very interesting. So that's really the mission of my lab. And I find it super exciting to collaborate with Melissa and Aaron about this. Also, interestingly, I like the word delays, because delays are very problematic for robots. A delay in a control loop is very much a problem. And nature has solved very good ways of handling delays, because our neurons are slow. They're much slower than electronics. And it's interesting how in our brain and our nervous system, we have ways of acting with delays. Maybe we can come back to that later on, but it's a very interesting problem of how robots have to handle delays. And so in my lab, we make all kinds of robots. We have swimming robots, walking robots, quadruped-like robots. And what you see here is an even simpler robot than our Salamander robot, which is an eel-like or lamprey-like robot. And one thing which is very important for us is to study this interaction with the water. And for that, we need good models and computational models. And we make a lot of work of studying the physics of the interaction and try to make numerical models of these interactions. And here, I think this is a perfect introduction to the work of Jonathan, who does his PhD and is an expert on this fluid dynamics.
Yeah, thanks, Auke. So indeed, yeah, for scientific purposes, the robots are very useful for validating the models we develop. Yeah, we use these numerical simulations as a complementary tool to the robotic experiments. So for example, here is a simulation. And in this video, we replicate the motion of the robot experiment that you just saw previously. And here we're using a particles method to simulate the fluid. This provides us with additional information that complements the robot experiment in studying the interaction between the robot and the fluid environment. So in the next video of the Manta array that will be coming up in a second, yeah, thank you very much. In this video, for our collaboration with Melissa and Aaron, we applied the same principle to the soft Manta model. And we set up this model in the simulation framework. We applied a motion to the body, and we added a flow to the fluid that comes in on one side and comes out the other. And so, showing the particles view, we get to visualize the motion of the simulated water around the model, where the colors that you see here represent the velocity of the fluid. And so we ended up providing this data to Melissa and Aaron for their work, which featured the different properties of each particle of the water. And Melissa and Aaron used this data then to produce the art that they are presenting.
Exactly. So thanks, Auke and Jonathan, for this introduction. And I think it's very interesting because it allows us to enter immediately on the specificity of our discussion, meaning the interest, of course, in robotics, on science and technology from very different perspectives and also with very different languages. And I think we went through also a sort of aesthetic experiment, because these data, indeed, that were produced by the Biorobotics Laboratory, they became part of the installation of Melissa and Aaron. But of course, I think through the process of our conversation and the discussion between the laboratory and Melissa and Aaron, there was, of course, a different take and a different interpretation of these data. So just to give also a correct framework, of course, we also focused on, we could say, the digital dimension of the work, precisely for the very specific context of the development of this residency. It was a remote residency. Melissa and Aaron had this creature already sort of integrated in their vision. And as you mentioned, indeed, Melissa, before, it was developed by the laboratory in Okayama. In this sense, it was also a sort of international sort of collaboration in some ways, but it allowed Auke to, let's say, and Jonathan and the Biorobotics Laboratory to experiment on a new, we could say, animal, but also probably allowed you, Melissa and Aaron, to sort of see additional aspects of this artificial part of your work, and sort of integrate it in your work. So what I thought was very interesting also to see today, it's you had, once you received this visualization by the Biorobotics Lab, which I have to say have in their color and the movement and through also the clear descriptions that Auke gave us, they really are very interesting scientific material. But what I found extremely interesting is that in order for you to integrate this gradually in your work and in the vision of delay lines and let's say the installation and its version for Nature of Robotics, this data translated immediately in, we could say, black and white. And we can now observe the first passage that you applied on this data. And you can perhaps tell us a bit of your reaction once you received this data and imagined how to include it and elaborate them further in the installation.
Yeah, so these images are based on the really beautiful and amazing simulations that the lab was making. And thank you, Jonathan, for all of the time and the crashes in the simulation and all of everything that you went through. But this is not imagery that's present in the installation right now. But it was a look at what happens maybe when you reduce, in a way, all of the information that's useful, and then do these simple kind of transformations of applying a linear key with a mat, which gives you this kind of stark image where there seems to be maybe more at stake, or there's a different set of stakes. There seems to be, this kind of conflict with this data storm around it. It's maybe a little more reminiscent also of like the motion studies of Etienne Jules Marais and also his smoke machines to study airflow. And so it's kind of it's more in that spirit. And then in the actual installation itself, the data itself became kind of embodied as a totally, as a new set of forms. So yeah, this was an interesting look at just how, how you could maybe kind of think about this, this struggle or this kind of the effects of the atmosphere, around it. It seemed to feel different.
And yeah, indeed, I think basically already in what you mentioned, so also of course the reference to more the cinema, we could say history, it's precisely interesting. I think it was also the experiment in the framework of the show to really establish a discourse, let's say, between science and contemporary art and also history of art. And but indeed, as you mentioned, Aaron, this was a sort of transitional step in order for you to start working on the data. And then this data actually, they ended up in a very, we could say, visionary and interesting visualization of the water environment around the Manta. And there's also, as we could see in the shortly in the initial video, there's a loop, basically a connection between a feedback loop between the creature, the soft Manta, and the visualization. So visitors in the space, they actually understand this connection between the movements of the Manta, as well as the change of this sort of landscape on the screen. So perhaps now we can indeed go through the final visualization that you realized for Nature of Robotics and for delay lines feedback. And you could tell us more, let's say, about this material, because here we might see that we could say that we had really this transition between extremely fascinating scientific data, but also a more, we could say, imaginary dimension that also, let's say, adds layers to the soft artificial robots that we have in the installation. And of course, we will see that at the end enters the more, let's say, complex aesthetics of the entire installation, which in some senses refers to the scientific dimension in also other elements, but mainly with, of course, an artistic and aesthetic approach to it that goes beyond the pure scientific data.
Yeah, I guess one of the questions, in this remote collaboration and focusing that on the simulation was, how does one simulation kind of consume another? And we didn't want to just represent the Manta that's already in the exhibition present there with the kind of simulations that the lab produces, the kind of visualizations, but we wanted to use the data that is embedded in there. So we worked with Ivalo Getov on the programming and kind of unpacking these really big data sets. I mean, I think some of those have more than 100,000 particles that are in, each frame of what's happening. So we worked with him to select a smaller number, about 5,000 particles, and each of the cubes that you see in this kind of cubic landscape are those particles. And I guess we kind of made this transformation from the visualization being about a simulation of flow to a visualization of overall turbulence, taking this velocity and turbulence data associated with the Manta as it moves through water and creating this other form that was distinctly different from the more biologic liquid environment, and creating this kind of cubic, geologic, crystallized environment that each cube has its own, autonomy and its own individual movement, but it's also a larger form. At the very beginning, you saw this kind of lobster tail or form that emerged from our first passes on bringing this data into the software Unity to work with the simulation that we had begun in the previous iteration of the project or the previous variation. And we wanted to keep this new form in this more crystallized area of thought, I guess. Do you want to talk?
Yeah, there's an incredible amount of data and information, which is it feels like it's still something that we can work with. It feels like we're just we're just kind of opening up some of the possibilities, and so some of the video, the black and white video, is really just a kind of a gesture, just a look at kind of how that felt. But within the world of this simulation, yeah, it feels like there's still that we're using there's an authenticity to the way that we're using the data, but we're still using that there's possibilities, so yeah, it still feels rich and alive, and yeah, and so and also going back to kind of this idea of the negation of what's useful, that's in no way kind of disregarding the important information that comes out of the simulation that the lab did. So it's not that's all still like valuable information that we're interested in using. So some of these kind of the throwing away of what's useful is more just a gesture.
I have to say that now I'm curious to hear, because I also think that in both in the universe of the data and visualization from Auke Ijspeert, even without, and the lab, even without, working, knowing a lot of this data, you understand indeed this density of information. And I think in this sense, probably here we can find also an interesting link between the data that the lab provided, but also indeed these other words that you disclosed as one of the many possibilities, as you correctly mentioned, of working around this data. But okay, I would be curious to hear, because indeed it was also the experimental aspect of this exchange. So what's your also thought when, I remember when we visited the exhibition together, and the question was, where are the data? But let's say also, what do you think, what's your reaction when you see, your scientific materials sort of shifting in this more different aesthetic dimension?
Well, personally, I find it fascinating. I love the display and the installation. So I find it very meditative and a bit psychedelic, a bit, and so really I could watch it for hours. So I love it. And interestingly, as scientists, we have the same problem. We have this overreach of data. We really have too much data all the time. And when we write scientific paper, we spend hours and hours how to make a figure, and that's readable in just one glance, and basically all condense this data in something very readable in a very short fraction of time. So we face the same problem, how to handle the data. So and I find it super intriguing to see this this data reused in other ways. So I find it super interesting. When I think about it, I think both scientists and artists, they explore the same thing. We're exploring who we are. I think an artist exploring by creating emotions, and we as scientists, we explore it by addressing questions, and at the same time we have the same goal of understanding who we are as humans, but also as animals. So I would really include the whole animal kingdom, even the living plants and all that. I think both artists and scientists are interested in that. So I found it very interesting in collaborating in that way. Another thing which I like, also what you said at the beginning, Melissa and Aaron, is this importance of softness, of soft robotics, the interaction with the environment. That's something roboticists and scientists start to realize, is our intelligence is not just data, it's not just data processing. That's only a minor part. The intelligence we have as humans or animals is the interaction and the embodiment, the physical interaction. We have a whole intelligence of the body that we can't completely underestimate. And interestingly, that's the most difficult part to replicate in a robot. The AI part, playing chess, is easy, but the embodiment, going on a bicycle, swimming, that's very hard. And I find it interesting that you mentioned these words, interaction, embodiment, softness. I think that's a key part of understanding intelligence and our adaptive behavior as animals and humans.
Yeah, the Manta acts as an interesting kind of translator. You get with a relatively simple set of ideas like move up, move down, you get this really kind of complex, kind of flowing, rippling effect that I'm sure, Jonathan, that was one of the things that you struggled with. I I wonder if it was because you kind of inherited this creature. You know, I wonder if it was. I mean, you had a basic 3D model, but it was almost as if you were studying an actual creature, in that the lab, you know, it was this kind of inherited kind of, you know, material. How was it working with this thing that was, you know, somewhat defined but had no motion attached to it, or anything that you added to it?
Yeah, challenging, for sure, challenging. I think everything that I thought I had set up and well understood with the eel model that I could maybe translate to the Manta, I very quickly realized it's not that simple. There were a lot of things to handle. As you mentioned before, there were so many crashes and things to change so that I could adapt it to the Manta. So it did indeed feel like I had to relearn, based on this model, a completely different form of motion so that I could run these simulations and finally get this data that we see in the videos.
Yeah, and there's a lot. I mean, the animations that you made, the model, there's still, you know, as I was saying before, there's still like all this really interesting material that you generated that we are working through. So yeah, so that's great.
Yeah, absolutely. That was indeed a challenge for me, handling the amount of data, how to illustrate it, how to actually get a video out of these simulations, which just run as code in behind the scenes, and translate it to something that is understandable. So
hearing your so there's the crashing, you know, there's the pain of the simulation crashing, but which, you know, is obviously kind of, you know, time consuming and troubling. But hearing that, there was I had a little bit of glee, or just a little bit of excitement, because there's that moment right before it crashes, and if you can capture the data, you know, I just remember working with like computer music systems, and this kind of overloading these things to the point where there's this moment where it's very complex, and then things die, but right before it dies, there's this like little chunk of stuff happening. So it was reminiscent of that. So anyways, I know it was painful, but it was also fun trying to see where the simulation started to like not explode, but like kind of derail. Anyway.
Yeah, fluid dynamics are definitely something that are very challenging to simulate numerically. We can even see a bit in the videos. Typically what would happen before when I would have these crashings is indeed particles that would start creating these kind of local energies that would create explosions. And I had videos where we would actually see water explode just before the whole simulation crashed because of numerical errors. But yeah, fixing these were really about solving one problem at a time until we got something stable enough so that the problem was achieved.
Okay, I also enjoyed hearing you talk about the problem of delay in these, you know, in creating robots, not only in the simulations, but that's a problem. And we had been, Aaron and I, thinking about delay lines as a kind of form of memory, as a way that, you know, another way to hold something or to capture something so that it can then be used later, and, you know, kind of making that physical. But I was interested to hear your coping with delay, or, you know, how you...
delays are very tricky in robots. And when you think about it, it's super impressive that we as humans or animals are able to do sports and move so fast, because our neurons are super slow. So if you look at the time that information flows in a neural network in our nervous system compared to a computer or robot, information flows like thousands of times faster in a robot, and we are very slow. So it's very impressive how, as animals, we are able to handle delays. And the typical control problem is like a thermostat. So if you want to heat the room, you are cold, you heat too much, and then it gets too warm, and then that's typically a delay problem. And many things have crashed in robotics or any machines because of delays. people playing with feedback loops and being too slow. And in robots and also in animals, the solution to that is to play with what's called feed forward and feedback control. So feedback has this delay problem, but feed forward is some kind of internal model of what would be good to do. And we have in our brain many of these internal models. So we know in advance what will happen, and that allows us to do fast movements. We don't need to wait back on delays to act. And a very important scientific question is this interplay between, in fact, this feed-forward thinking, which is the central nervous system, and the sensory feedback, which is the peripheral nervous system. And this is interestingly a key question in neuroscience, how this interplay between the feed-forward aspects and the feedback aspects. And that's the only way of how robots and animals handle delays. So I like this loop that you mentioned in the delays. And indeed, the delay is a memory because it flows through the system and it creates patterns that are due to delay.
Your analogy of the thermostat also, there's another type of delay happening where, this fluid machine, this computer that's cooled by the water that it's using to make a simulated water, the heat is being dispersed through this kind of system, the artwork as this system, and being offered to this artificial life form. So what that environment creates, whether, it's performing a function for the machine, but not necessarily for this artificial creature, but this kind of kleptothermy of the reptile is happening there as well.
Yeah,
delay.
The delay line becomes a cooling or way of transferring this energy from to the Manta.
Yeah. So how hard was it for you to tune these delays, or did you compute them, or you just a bit by trial and error found what was good?
I mean, for the water system itself, it's that's very it's very, very much kind of an organic, it kind of comes out of the system itself. At EPFL, it's a closed loop. So there's less of, it's a different set of references, right? It's kind of more internally interactive, a bit more, almost like more of a hallucination of the Manta. The simulation is like this, kind of this proposed vision, this extended organism in a way, and that the computer becomes the way of creating this hallucination. But the delay line around it, is very much, it changes. It very much changes. It's not precise in the sense of like an audio delay line or a microwave delay line, or at this point.
I think it's the water, the fluid has to reach an equilibrium between all those forms, and that shifts a bit, especially in the beginning, and then it seems like it kind of reaches an equilibrium. Mm-hmm. One of the things I also wanted to mention about, how we came into soft robotics, or what was interesting about soft robotics was, the project Delay Lines is also a kind of material study, or a study of transformation of a particular material. So we had been looking at glass as this material, which is formed from silica. We work with computers, so you have silicon chips and this kind of mineral necessary for computation. And then most soft robots are made from silicone. And we were interested in how this material is present. It's ubiquitous throughout the world. It's one of the most ubiquitous elements on Earth. But in these materials that we're using, silica kept coming up. And obviously being transformed by all these different processes was another reason that it spoke to us versus the motors or robots that we had been looking at before.
I was also thinking, thanks to all, because it was extremely interesting, this exchange, because it really shows the potential of this exchange, both from Auke's point of view and from you, Melissa and Aaron. Really, we are starting investigating, I think, the extremely the fascination and the interest of precisely this kind of dialogue, because there are many resonances. I mean, of course, the systems that Auke refers to, or the feedback or the delay concept that Auke refers to, correspond to also other dimensions, let's say, in the field of art, or, I mean, your work and how you developed and worked around these ideas. I was thinking perhaps we might actually now re-see a few images of the work, just to have also references exactly. So we see here, yeah, this wonderful installation that we realized at the EPFL, in which indeed we have both this research indeed in, of course, soft robotics and Manta ray, but also this reflection around materials and silica. And perhaps Melissa and Aaron, I mean, really going through these images, you can, because of course we have here not only what we addressed so far, so the machine, the robot, the feedback, the system, but also we could say even an aesthetics which reminds also of the world of the scientific glass. With everything, it was a very specific glass that we used for the installation. So perhaps through these images you could go through a few elements which indeed, let's say, we have both this idea of the machines, of the feedback among the different elements and the flow of water and a system, because we had this sort of central also computer brain, but also this fascination for materials and further investigations, we could say, of the aesthetic scientific realm that you realized through the work.
So the square glass coils are speaking more directly to these delay lines, or this kind of explicit delay, and the air bubbles being a very important part of being able to see that. Without the air bubbles, it just appears more transparent than if it was actually empty. And then some of the other glassware we were kind of chose or working with for different reasons.
A lot of so we chose forms that are typically used in labs, but we maybe made a transformation in scale of that particular apparatus. We chose mostly apparatus that when we looked at them had some relationship to interior body shapes, forms, organs, some look more direct than others. We also made a lot of organic shapes ourselves using this borosilicate glass. But I think our first introduction to scientific glass was watching someone make a condenser coil. And we had this moment of feeling like we really focused on the time that it took for this object to be created. So this idea of delay line or time present in formation of an object was really there at the genesis of our introduction to flame workers and people who create scientific apparatus. And then we learned from some of these engineers and artists who work with this material to make more organic forms, which are also kind of interconnected in the piece. And so that's how some of the selection of the glass is made or chosen. And I guess I want to maybe say something about the water as well. You know, water was important maybe initially in our invitation to Okayama. We were inspired by the site. We were next to the Asahi River, and part of the simulation is imagining the subterranean river that was providing the water source for the city. But water is this kind of, you know, it's our first home, and it's this site of transformation, embryonic transformation, but many types of transformation. And I think in relation to silica, water and silica have a long geologic history of being in concert with each other to create these transformations. So it was interesting for us to begin to work with machines that needed this, you know, liquid, and also to then work with a kind of simulated liquid. And we found it really interesting that in the Biorobotics lab also they were working with swimming animals, or animals that had, you know, salamander walks on land and then also swims. And of course we have the tank, because, you know, how do you bring a robot to life? You need a tank, right? Frankenstein told us this. So there were a lot of connections just formally that felt like, when we gave Jonathan the model to see our Manta in the tank also was like, of course, they need a tank too.
It's interesting. I remember when we discussed this water element, and we also thought that at the EPFL makes also a lot of sense because the campus is in front of the Lehman Lake. So the lake, water is really a presence, let's say, also in this location. So it's very coherent, let's say, with the context. But I think basically we have now the premises to continue for 3 hours, but we have a limited time. But I have to say, again, the experiment we conducted last year and really this collaboration was really exceptional. And I think through our conversation, we had already the beginning, let's say, of the extremely interesting reflections that we can have at the crossroads of, we could say, different disciplinary fields, and what also Auke mentioned at the beginning, so this sort of common ground sometimes shared between artists and scientists, which I found in Nature of Robotics also in the realm of speculation, but also observation of nature. And I remember, Auke, when we also discussed about the ultimate, let's say, still aspect of the biorobotics research, and how you mentioned that still basically the natural world, there is a mystery that you are trying to, let's say, discover and of course study and implement in this artificial realm. And of course, Melissa and Aaron, this transition that you mentioned, because indeed in your background, there's not, let's say, soft robotics, so this interest in more, let's say, biomorphic forms arrived at some point in your research. So I remember also, I think you worked also with the Vasulka in your past, exactly, and I think that was a very interesting element also curatorially for the show. Stena and Budi Vasulka were, for Auke, really important figures in the field of media art, and actually really experimenting in this sort of adaptation of robotics and machines and systems in the framework of contemporary art and art history. But so I think, again, today we touched on the potential of this discussion. And let's say we know that Melissa and Aaron, you will develop your research in the next year. So I think it's going to be, I really look forward, because I'm sure indeed that let's say we had a year, but it was not enough indeed to disclose the potential of this data. And again, it was really exceptional to realize this collaboration at the EPFL. And Jonathan, of course, with your contribution. And I really think in our discussion today, as well as in the installation that we realized, and now is going to travel in Europe, it will be presented also at the Center for Custom Media in Karlsruhe. And I think really it's amazing how through this work also a complexity of discourses, and really, let's say, the different story of the exchange between artists, scientists, and engineers, sort of, we can continue to sort of develop this kind of discourse. And again, I thank you all very much for this conversation and for this project. And I look forward basically to observe your research in any, let's say, both in the scientific and in the artistic direction in the next years. Yeah.
Thank you very much. And we will, as you said, the piece is traveling, and so all of this data and all of this work and study that the lab made will, we will continue to use it. So
I think the exhibition is not a culmination of something. It's been a point of some sort of crystallization, but definitely what's been so generous about the residency is that we didn't have to end here. We can continue our exchange, and that's been really amazing. Thank you.
Yeah, for me as well, it was super exciting and really stimulating, fun also, and cool. And I have to say, for me, it was the easy part because Jonathan did all the hard work, and we underestimated how much work it was, but he did an amazing job. So thanks a lot, Jonathan. You are my hero.
Jonathan, you definitely you did a lot, and more will come from it. So don't just understand that we're just opening it up.
Yeah, thank you, and I'm really looking forward to the next steps. Yeah, I think this is really exciting work. So looking forward to it.
Great. Yeah, thank you again.
Okay, so with this and with the background of the EPFL Rolex Learning Center and Agora, thanks a lot. Have a good continuation of your evening and of your day, Melissa and Aaron. Of course, we could find a good meeting point. And thanks again and greetings from the EPFL pavilions.
Thank you all.
Thank you.